Well, hello friends. Welcome back to the program. Today we are going to run Serenity OS under constrained conditions and see how the system behaves and what we can do to make it behave better. And the condition I had in mind was less memory. So currently I usually run the system with 4 gigabytes of RAM. So there's this environment variable you can set that just causes our script to assign that much memory to the VM. Now, if I take that down to, let's say, 1 gigabyte, and then boot Serenity, everything is still fine, although we can see that we are at about 350 megs of the gig in use. So 350 after startup means that we should still comfortably be able to do 512. Yeah, so 347 out of 472. The memory graph is now like looking pretty busy down here already, just after boot. So, but it's still booting and working just fine. But what if we crank it down to 256? So well below the actual typical footprint after boot. That was not very successful. So this is exactly what I was hoping to find. So we are crashing in the kernel, which is super not cool. We should not crash the kernel just because we run out of memory, unless, well, we should try to make our kernel resilient to that under all conditions, as long as some initial amount of required memory is available. But we are far from that. So let's see what happened here. So some process is telling us to mmap something, and we try to allocate a region for the mmap, but things go wrong because we have no physical pages available. Right. And I notice it says no user physical pages available, which is actually outdated terminology. So let me go ahead and update that right away before anybody else gets confused by it. Let's see. Okay. Kernel. Fix outdated physical pages terminology. Update. These are now just physical pages. Yeah, so we used to have a distinction between supervisor physical pages and user physical pages, but that distinction was removed recently. So now there are only physical pages, and they are used interchangeably for all purposes. Anyway, so we had that error that there are no physical pages available. And because of that, I guess it leads to us being unable to allocate a page table. So we can't even allocate a page table. That's a pretty messy situation. So I know that we are not very good at thinking of ways to free up physical pages. I think in the past, whenever we would run out of physical pages, what I would normally do is just increase the amount of RAM in the machine, in the virtual machine, and then think like, oh, future Andreas will deal with that, or future somebody. So I guess this is future Andreas reporting in, and we need to do something about that thing. So no user physical pages. This is the error that we want to. No physical pages available. We need to do something about that. So it comes from this function right here, memory manager, allocate physical page, which either returns one physical page or an error. Okay. So it operates by calling find free physical page. And if that doesn't work out, we didn't have a single physical page. Let's try to free something up. Okay, that's promising. So first we look for purgeable VM object in the volatile state. Sure, so we look for something that we could purge and reclaim memory. And if that works out, we would print out purge saved the day. Okay, so did we actually print that out? Purge saved? We did not. So I guess we didn't have any purgeable memory at this stage. I mean, it's pretty early during boot, so maybe it's believable that there is no purgeable memory in the volatile state yet. Let's see. So if it's not purgeable or it's not volatile, we skip it. Otherwise, we try to purge it. What does purging do? It looks for... Oh, so if it's a volatile VM object, then we will release all of its pages except the shared 0 pages. Okay, well, that seems reasonable, but I guess we didn't have any of those. And if purging fails, then we say no physical pages available. So basically, the only thing that we do when we have no physical pages is we try to purge volatile memory, and it seems like there isn't any, and then we just fail. So that's where the enomem comes from. So there are a bunch of different things we can do here. The first one we should definitely do is if we have files mapped into memory that are not even mutated. So like clean file-backed memory. Like if you have just mapped an executable into memory, you didn't modify it in any way. So it's exactly the same as you would find on disk. We should be able to just throw that out because you can always page it back in from disk, right? So I think it's telling that it says first here because it's just begging to add a second. We look for a clean file-backed VM object. Or we look for a file-backed VM object with clean pages. So because if clean and dirty in this context means that if you map a file, but you map it writable, and then those any changes that you make to that file should be eventually reflected in the disk copy, as long as it's, I think it's map shared, prot write. It might not be synchronous, like you have to maybe msync or something like that, but let's skip that, those type of pages right now, because we don't do a lot of those anyway. So we should do those eventually, but at the moment, let's focus on just finding out if we have some clean pages. So clean means that they are, for our intents and purposes, identical to whatever's on disk. So let's see. So if, I guess we could do this in a single loop over, but maybe it's a bit more expressive to do it in a is inode. Let's see. Is it favorable? Like, I'm thinking, which one is better? Like, do we prefer to purge volatile pages or release clean file-back pages? I don't know which one is less disruptive. It's probably less disruptive to release file-backed stuff. And so, I mean, it really depends on if you're releasing a file that's being accessed often, then you might be screwing yourself by freeing that. But likewise, if you're, we don't have enough information about like the popularity of the memory pages at the moment because we're not tracking enough interesting data about them. So let's not worry about that right now. Like, we'll just make a stupid choice, and then we can add more sophistication later. But for now, we just need to freeze something, right? Because we don't want to crash the kernel when this happens. We want to continue and then fail in user space at least. So let's see. So let's cast the VM object that we have now verified. I can't spell. VM object that we have now verified is a inode VM object. Inode VM object. VM object, sure. And then if inode VM object is shared. Yeah, if it's private. Oh, wait, we have release all clean pages right here. Interesting. So I guess we can just do that. Yeah, it doesn't matter if it's shared or private. If we have clean pages, we should just let them go. So let's see, what does the purge path do? So if purge page count equals purge, then, well, we actually purge like everything we can from that object. That seems a little bit excessive in the inode case. Like, if one page is enough, maybe we should only do a single page. But we could try also releasing everything. Let's start by just releasing everything. But keep in mind that the API that we're working on here is allocate physical page. So this function is only expected to return a single physical page. We don't need to free up 100 physical pages if one is enough. But it would be more complicated to pick a single one. So since we don't have API for it. So I guess we would, let's just mirror what we have upstairs. So least page count. And then we'll print something similar to what we saw above. Release clean inode release saved the day. Recovered pages from inode VM object. Yeah. Are released. And then we should try to find a page once again. I think we are holding a lock here. Yeah, we're locking the memory manager, so nobody's going to come here and interleave, messing us up. And then I guess we want to verify that we did indeed find a page, because if we freed something, we should be able to find at least one physical page. And we should be able to break here. Yes. Okay, so let's try this out. Yeah, it's really unfortunate to release like all the clean pages for that inode. Okay, all right, so we booted up to a GUI, but it doesn't log into the desktop. That's interesting. So we have assertion failed, network servers not spawning, and then we have pausing spawn out of memory. Okay, interesting. Wait, why would we get out of memory? But there's no like error. I guess maybe there isn't enough memory that we can commit to forking. Let's see. So down here it says purge save the day. So purging 12 pages was able to save the day ones, and then clean inode release saved the day with a 71 page nuke. So I think what happened here is that we started up some processes, but not all of them worked out. And let's see what's actually running here. So we have Windows server is up. We have the login server, I feel like. Wait, what's it called? Is it not called login server? Am I not seeing it correctly? Oh, did I kill it by doing that? Oh, shoot. Oh, Windows Server died here. Interesting. Okay, yeah, so there's all kinds of trouble. Key map switcher 95. Maybe it doesn't like me switching out to console mode, actually. What's key map switcher? 95. Verify not reached. So we're trying to open proc key map and that doesn't work out. Ouch. So I wonder why that didn't work. I wonder if it's reproducible. So still boots into the login screen, sure. And then key map switcher once again. Interesting. I kind of want to know what the error is. Let's see if we can find that out. Hello error. I mean, it feels like it's going to be some kind of a memory related error, right? But it'd be nice to get that confirmed. Okay, so we're trying to open proc key map when I press something. Out of memory, sure. So we don't even have enough memory to open a measly little file. Cool. Yeah, so I think the issue now is that user space is up and running. The kernel is not buckling under the stress, but there simply isn't enough memory to go around all the processes that we want to launch. So, you know, it's a sticky spot, but it's definitely better than where we started. So let's go ahead and commit that. Kernel. Oh, actually, I want to add a fix me to that. I want to say something like fix me. It seems excessive to release all clean pages from the inode when we only need one. Yeah, exactly. Kernel. Free release some clean inode, clean file backed pages when starved for pages. So until now, our only backup plan when running out of physical pages was to purge volatile memory. Was to try and purge volatile memory. If that didn't work out, we just hung user space out to dry with an enomem. This patch improves the situation by also looking for clean file-backed memory pages that we could trivially page back in from disk. That we could, let's not say trivially, but that we could page back in from disk. As well, by also considering by also considering clean fallback pages as well. Maybe the as well is redundant with the also. Okay. This could be better in many ways, but it already solves, already allows us to boot to Windows Server with 256 megabytes of RAM. Yeah. So that's cool. Okay, so I guess I would like to find out, it would be cool like when we're failing like this. So this thing here, like essentially the first failure that then cascades, it would be sweet if we could do like a little kernel dump. So if we are, you know, fresh out of memory, we could sort of just dump a list of processes and some basic stats like how much resident memory, how much shared memory, so on, just so you can get some kind of idea, I guess. Because we have this display, but this is only relating to the scheduler, and also it doesn't come automatically. You have to provoke it to print that out with Alt-Shift F12. But I think it would be sweet if we would just print something out. So where does the enomem come from? Could be a number of places. Sure. Let's go look in memory. Oh, we are a memory manager. Enomem. Let's see. Commit physical pages. So, right. So which probably here, actually. We didn't see this, so we're not here. Allocate contiguous. It's really mostly really only the kernel that asks for contiguous pages, and we are failing user space. So not those. So yeah, it's going to be this one, I'm pretty sure. But let's log something here. Can't. Let's see. Can't commit pages. Have only page count and system memory info, physical pages uncommitted. Let's see. Of course, a cheap tactic, or not cheap, but the classic tactic out of the bind that we are currently in would be to add swap, which would then allow you to just spray your disk full of memory. But I would like to explore ways to avoid that if we can. So let's see if this actually prints. Can't commit 16 pages, have only 8. Ooh. That is not enough. Okay, so we are scraping the bottom of the barrel for memory pages here, and it's not working out. So, what if unable to commit pages, have only and then here, what if we did ourselves a little bit of a dump? So process const process, I guess. Okay, I have not worked with these data structures for some time, but let's figure out how to do a simple debug print here. So process and PID, and then I guess we can just print out like how much resident shared virtual Just, you know, the basics. So process name, process PID, process address space, resident, and shared and virtual. All right. Let's see. Let's hear it. Because I just want to know, like, what's taking up all that stuff. All right. So, I mean, it's something. It's kind of chunky. It's hard to read these because these are in bytes, not the... Yeah, bytes is not the right unit here. Like, we just care about pages. So let's just do this. That's a constant, so the kernel will turn that into a shift anyway, before anybody starts sweating the division. Come on now. Yeah, I was just thinking, like, is this excessive to dump this out when we are fresh out of pages? But I think this is probably useful information. So I'm gonna leave that in there so that we can see. So what are we looking at here in terms of resident pages? Do we know how much committed a process has? I don't know if that's really calculable since it can be shared across forks and stuff. Yeah, I mean, we're gonna need to do some better math. Probably. Not gonna get into that today, but yeah, probably don't have stats for this kind of stuff. So the way our memory system works currently is that when you allocate like 64K with malloc, for example, then the system will commit to commit 64 kilobytes worth of pages to your process or to you. So it makes a commitment at that point, and that commitment means that nobody else will be able to take those pages from you. Like, the commitment will always be honored. That's why we are getting out of memory errors, because there are just too many commitments to other people already, and we don't have enough memory to commit something to you. You being network server, in this case, the process that wants to allocate. So, yeah, I think we're gonna leave it here for today. This was a nicely bundled little fix. So let me go ahead and add this logging. Kernel dump dump list of processes and their memory usage on when ooming. When enomemming, let's say, or when enomemming. What do we call this type of when ooming? Yeah. Let's see. Yes, I think we're gonna wrap it up here. I'm happy with the progress. Like, we got the thing to boot, and we have our little dump, and now we need to put our thinking caps on and come up with some interesting strategies for this. but I don't have anything obvious that I want to do right away. So I'm going to leave it there. So this will be the end of the video. If you made it this far, then thank you for watching, for hanging out. I hope that you saw something interesting here, and I'm going to try a different size. Let's try 300 megs. Yeah, see how that goes. Ooh, then we get some totally other kind of thing. But still, we're still failing to commit. Although now we're crashing in the kernel instead. That's pretty nasty. Fail to spawn desktop sucks, dude. Oops. Sucks, dude. So what happens if we fail here? Then this function returns. Yeah. Anyway, seems like there's more errors to be tracked down, but we're already closing up shop. So thanks for hanging out, and I will see you next time. Bye.